Today I'm going to introduce you to some assembly language programs for this 8031 system, or 8051. It's actually an 8031 microcontroller, and this system also has some LEDs that are attached to it that we could light up. So I'm going to run some programs in assembly language and go through them, walk through the programs, and go through what the programs do and how they work. And previously I introduced the system in another YouTube video that you could watch if you wanted to find out more about this. So this program is called exam2.asm, and the object of this little program in assembly language is to set all the external RAM to a fixed value. So the external data RAM in this processor is 64K. So in this program, this is the whole program shown here. This is the value. The first line here is the value. We're going to set every data location, every memory location to AA hexadecimal. And so the beginning of the program starts at 800 hexadecimal. So that's where the user external ROM starts in this program. So the first part of the program is to set the data pointer to 0. So this is the first address in the RAM address for external RAM is 0. So over here, this instruction here, this is the high data pointer and the low data pointer. Now the data pointer is 16-bit, but this is an 8-bit processor. So we take the high part of the memory of the 16-bit data pointer and put that in register 1. And then we take the low part and put it in register 2. So we're going to need this because we need to know when we're done updating this RAM. There's 64K bytes in this RAM that we have to update. So this is a little algorithm that counts to the 64,000 and sets everything to AA. So the first part is to move register 1 into the accumulator A. So the accumulator A it stores register 1. So this is actually some logic to determine when it's done, when it goes through every point in the RAM. So it starts at 0000 hex, and we want to end at FFFF hex. So anyway, we move register 1 to the accumulator, and then we take register 2 and we AND it. So we're trying to determine when the data pointer is set to FFFF, we're going to increment the data pointer. So when the data pointer is FFFF hexadecimal, that's when the program ends. So we put that. So if it is at the end in register 1, FF will go into A, and then FF will be AND. So if both of these are FF, then the accumulator will have FF. Otherwise, it'll have something other than FF. Then we're going to take the complement of the accumulator. So if A does have FF, which means it's the end of the data pointer, we'll get a 00. So now here's a jump. So if the accumulator is not 0, if it's not 0, that means we have more that we need to write in. It's going to jump to label 1. But if it is 0, then it's not going to jump to label 1, and it's going to jump to label 2 and then the program, which means at this point over here, it means all the RAM has been updated. So there's a loop here that starts here, jumps to label 1, and there's a loop that goes around and around until all 64 kilobytes are set to AA. So what happens here is that it doesn't, if the accumulator is not 00, it means it's not done. So it goes from label 1, it skips over here. This is a short jump. This goes to label 2. When it's done, when it is 0, it'll skip this part and jump to here. But if it's not done, it's going to move the value to the accumulator. So the value is AA is the value. So it moves that to the accumulator, and then it takes the accumulator and does an indirect to the data pointer. Now MoveX is a special move that moves to external RAM rather than to the instruction or program RAM. So the next step is to increment the data pointer. So if it's going to start at 0, so the next point it's going to go to 1, and then jump to label 3 and start up here again. So up here, it's going to load these two, the data pointer into register 1 and 2 again. So say on the first go around, the data pointer is 1, so it's going to load a 0 into register 1, a 1 into register 2, and then it's going to move the 0 into A, then AND it. So this is all going to be 0 because AND with 0 to 0, 1 is a 0. That's going to complement the 0, so there'll be something other than a 0, 0 here. So it's not going to be 0, so it'll jump and increment the next one. So it does this for all 64K. So we're going to demonstrate this in a second. So what we first have to do is load this program into our system. So we do that. We have a TerraTerm running that's communicating to the processor. So we're going to load the hex file that has the program in it. This is a very small little program. So we press E here, and we're going to turn on the write enable, and then we're going to go send the file to load the program. So we have to find the file. So the file is in this little DOS directory that I have it in. I got to get there, and let's see, we're there. So this is it's called examp2.txt. So it's right here. So the program is being uploaded. It's a very small little program. Okay, so now we're going to check the program. So we type K to check the program. So we do the same thing again. We'll send the file, and just to verify that it got loaded. So we're trying to find this examp2 text, which is the hex file. So it says good checksum, so that's all good. Okay, so the first thing to do is let's look at our what's in the external RAM right now. So we give it an X command. So the first block, it's all kind of random data in here. It's not A on the first block. So this is 00 to F0. So let's look at the very end of the data. So we're going to type an FF here, and likewise it's the same thing. So now to run the program, we type the J command. So we're going to hit J, and it takes a little time, but it comes back to the monitor. And now we'll type X again and look at the first block. So you see how all these are A's now, and we'll look at the last block, which is X, FF, and so everything was set to A, so the program worked. So the next program is a very similar program. It's called examp02a.asm, and this is identical to examp02, except it's going to write out a message saying that it's initializing the external RAM. So it does take a little time to do this because it has to do all 64,000 bytes, and it's not the fastest processor. This is like maybe a 1 megahertz, 1 microsecond frame time, instruction cycle time, so it's a very slow old processor. So anyway, in this program we have a thing called write string, and this is inside the monitor program at location. There's a subroutine there at location 77C hexadecimal. So what's going to happen when this program first runs, it's identical to examp02, but when this program first runs, it's going to write out this message. So it's going to borrow a subroutine that's already in the monitor program. So all it has to do is a long call, and then what you do is you put in the message you want to write with some line for each carriage returns, and the escape character means that it's done. So likewise, we have to load the program again. So we're going to go load this program. So I'm going to type the E command, and now I'm going to turn on the write enable, and I'm going to load the program. So I hit send file, and so I'm looking for examp02.txt. So I hit that. So now it's loading in. It's a little bit longer than the program we had before. So now I'm going to verify the program by typing K and doing the same thing again to make sure our checksums are good, that it actually got loaded. So it's a little test to verify that it got loaded. So we're going to run that. So it says good checksum. So each line it checks, so the whole thing is good. So I did a power cycle on the processor. So we'll check that RAM again. So I'm going to hit X and 00. So you can see it's all kind of random data, and we're going to check the end of it. So I hit X, FF. So we want to set all these to AA, and everything in between gets set to AA. So the way we do it is we type the J command, and except this time we'll get a little message at the beginning saying that's going to initialize the data, and then when it's done, it'll jump back to the monitor program. So I'm going to hit the J command. So there's our message, initialize external RAM. So I went back to the monitor program. So we'll check, and we'll look at block 0 now. So you see how it's all A's, and then we'll check block FF, it's all A's. So let's check something in between. We'll check, say if we check CC, so you can see they're all A's. So that program worked pretty good. So the next program we have is going to write a binary counter to those LEDs, those red LEDs. And this is another really small program. And so this is a very simple little program, and it has a little countdown timer. I had to put a delay between each change to the LED because it's so fast you wouldn't be able to see it. So the way this program works is called example3. You set up a countdown timer. Okay, so there's one little countdown timer, and the highest I could set this to is FF. So it's going to count down all the way to 0, and when it goes to 0, it's going to increment the port 1 that goes to those LEDs. So likewise, this program starts at location 800. So the first part is this register 1. Now register 1 is going to reflect port 1. So the first instruction here, the first real instruction is to set register 1 to 0. So we set register 1 to 0, and then we write register 1 to port 1, which will set all those 8 LEDs off. So the next step here is to initialize the countdown timers, because we want to count down from FF to 0. We want to add some delay, otherwise this would be so fast you wouldn't be able to see it run. So this is set to FF, so we put FF into accumulator A, and then so now the next instruction is a jump if 0. If A is 0, you jump. So A isn't 0 initially; it's going to be FF. So it's being it's FF, it's going to take this path and keep running and decrementing A until A is 0. When A becomes 0, then it jumps to label 3, which increments register 1, which is the counter that represents the lights. So once it increments register 1, it does a short jump back to label 1 that moves it into port 1. So it does the same thing again when it goes to 2 and 3 and 4. So this goes all the way up to FF, and then it starts over again. So it's a very small little program here to light the lights. So it represents a binary counter. So we're going to load that program now in the same way we've been doing it. We type a E command. So we hit E here. And we got to turn on our write enable. And so we're going to send the file. So we want to find examp3 text, so we'll do that. So the program loaded. It's a very short little program. We'll do a check of it, and using the K command, which is a check verify routine. That's in the monitor program. So we'll run that. So we get a good checksum there. Okay, so that's good. So now to run the program, I just type J, and we're going to take a look at this once it's running. So I'm going to hit the J, and it's running. So we'll go take a look at that now. So this is a demonstration of the binary counter example3, and as you can see, the 8 lights are lit, and you could see like maybe the last 3 lights are blinking, maybe the last 4 lights. Now the first lights you can't really see blinking. That's because there's not enough delay in there. It's just so fast. Even though it's FF, which is 256, running at a megahertz, is still very fast. So that last light is blinking very rapidly. So we need to add a little bit more delay to this if you want to see the effect of the binary counter. So the next program is called example3B, and it's the same as before, except we have 2 countdown timers in a row. We're trying to slow down the delay, so it's similar to example3, except we use the countdown timer twice, so we have 2 in a row. So that should put twice the delay that we had before. So we'll go run that right now. We'll load it and then go run that. A little more complicated, more labels in it. And I'm going to put this on my website and make it all open source so you can download it and look at these simple little programs at your leisure if you want to learn assembly language for the 8051. So let's go load that now. So the way I have to do it is I go back to TerraTerm, and I'm just going to hit a reset here and just hit N just to make sure our communications is good. Okay, so we're going to hit the E command, and we're going to send the file. And so now this is examp03b.txt. So we got that. So we'll load the program, and it's loaded and done. Oops, I forgot to hit the right enable. So let me hit the right enable and repeat that. And so otherwise it doesn't load unless I have the right enable on. So I have the right enable on now. And here it is again. So we wrote into it again. So now we'll do our check. If I did this check without the right enable before, then I would have gotten errors. So I'm going to do the K command and send the file. And I need examp03b. Hopefully I loaded the right one before, otherwise I'll get some errors. So good checksum, so everything's good there. Okay, so we're going to run this again and demonstrate to see if we could see if the delay is any longer than before. So we'll do that. We'll type the J command, and we'll take a look at that now. So this is program examp03b, and as you can see, yeah, it is slower. There's more delay now. You could see maybe the last 4 or 5 LEDs blinking, but it's still not slow enough. I need more delay. So I'm going to do, the next time I'm going to do a nested loop to try to get more delay so you could see this binary counter a little bit better. Now we have examp03d, and this has a nested loop in it, so it's a countdown loop within a countdown loop. So the first one we set to FF, which is the max, and the next one we set to 80. So there's some more flexibility here. I found that FF is too slow, but 80 is pretty good. So like again, it starts at location 800 hexadecimal. So the first part of the job is to load these initialize these countdown timers delays that are within the system, so we could see the binary counter slower. So we set register 1 is going to set to FF, and register 2 is going to set to 80. So then register 3 represents what's in the port, so we initialize that to 0. So this, now we're in our main loops here. So we move register 3 to port 1, which lights those lights. So this is the countdown timer. So this is a instruction. It's called decrement till it's 0. So register 1 has a FF in it. So it's going to go through here, and if it's not 0, which initially it's FF, it's not. It's going to come through here, and then it's going to initialize the first timer here. Okay, so register 1 starts at FF, so it's going to move FF again to register 1, and then register 2, which also has this 80 in it. It's going to run this. It's going to run back and forth and down here. So it's going to jump when it's going to start at 80. It's going to start at 80 and then come here. But this is going to decrement it every time. So first it's 80, then it goes down 1, so it's going to go to 7F, and then it's going to jump here, and it's going to keep decrementing until eventually it's 0. So once it's 0, it resets the timer back to 80. Then it's going to work on this one over here. So it's going to keep decrementing this one, register 1, until that's 0. So when that's not 0, when that's 0, so what happens is that it keeps there's a loop here. So what happens? It's going to decrement it. So when it's not 0, it's going to come through here, and then go through here. So it's actually this one here. This is kind of like the added nested loop. So eventually this will run down, and then this is going to increment register 3, and then it's going to jump back here and load register 3 into port 1. So this will give it a much more longer delay time than we had before. So this is another little program. The nice thing about assembly compared to compilers is very efficient. The compiler has a lot of overhead, so if you want to do some very efficient programming, program in assembly. So we're going to load that program next. So we go back to our monitor program, and we're going to type our E command and turn on the write enable, and we're going to send that file. So that was called exam03D. So here it is here. So we're going to load that, another small program. Now we're going to go verify it. So we turn the write enable off, and we're going to go verify it now. So we're going to send the file again. So we load it, then we verify it. So we're going to verify it. So it's all good checksum. So we're going to run that and take a look at it again, and we'll see that it's much slower now. Yeah, so now you can see that it's incrementing at a much slower rate. So we have a delay within a delay. So that you could see, you could actually see the first light blinking there, which is represents that delay on a delay. And so this is a nested delay loop, and you can see the action of the binary counter. It's a 8-bit counter that goes all the way from 0 to 255 and then repeats itself over again. So we had to add a lot more delay in there to be able to see the effect of the binary counter to verify that that was working. So the next program we have is called example4.asm, and this is kind of to demonstrate it like an if statement in assembly language. And we're also going to utilize our monitor program to write out some messages. So there's a value here we set to 80 hex, and we're going to have a variable that's a counter that's going to compare against this value, and if it's equal to the value, it'll put out a message saying the value is equal. If it's not equal, it'll put out a message saying it's not equal. So this is kind of like a comparison similar to an if statement. So anyway, we start the program at 800, and so we're going to register 4 is going to be our counter that we're going to compare against our value. So we initialize that to 0 here. So this is called the CJNE statement. So it's a compare and jump if not equal. So when it's equal, when it's not equal, it's going to jump here and write out this message: the value is not equal. But when it is equal, it's going to skip through and jump out and write out the message is equal. So when this is equal to 80 hex, it's going to take this path and write the value is equal, and then it's going to jump around here to an increment. It's going to increment the register 4. So the register 4 is going to start at 0, and then it's going to increment. So it's going to start at 0, 1, 2, 3. But when it hits 80 hex, it's going to say the value is equal. But all the other times, when it's not equal, it's going to jump here, and then it jumps around. This is the main loop LO1. And test it again. So this is another little program to try to demonstrate something like an if statement logic branching for assembly language. So anyway, we're going to go hit a reset here and just hit the end command. So we're going to load the program again with our E command, and we hit our write enable. So we're going to hit send file and look for example4.txt. So we're going to load the program. A little bit longer program because it has some ASCII text in it. So now we're going to turn off our write enable, and we're going to do our verify here, and we're going to hit our send file and look for exam4. And so it's going to say good checksum, good checksum, good checksum. So that's good. So now we're going to run it. We're going to hit our J command here, and so you can see it's not equal, and at one point, you can see that equal there. So the next time I see it, I'm going to hit a reset to stop it. So let's see, okay, stop it. So you can see in here that value was 80 at that point, and that's when it said it was equal. But when it's not 80, it's going to say it's not equal. So anyway, that's a demonstration of an if statement. So example 04A is a little variation on it in that it's going to also run the same program again, but it's going to write out the value, the byte, the variable R4. It's going to write that out. So it's going to vary from 0 to FF, and when it's 80, it's going to be equal. So we'll go run that one. So we'll go back to our monitor program here and just do a little check, make sure our communication is good. So we're going to do our E command. So this is our program 4A now. Let's see. So we're going to send the file, and we got to find 04A.txt is right here. So we'll load that program. So we're going to turn our write enable off and verify that it got loaded properly. So we'll say send file. So 04A.txt. So good checksum. Good. I'll get a bad checksum if there was an issue. So that's good. So now we're going to type our J command again. And so now it says the value is not equal, but when it hits 80, it's going to be equal. So we'll let that run through, and I'm going to hit a reset when I see that it's equal again. Okay, right there. So you can see the value. It's going all the way to 7F, and when it was 80, it said that it was equal. So that's an example of an if statement. So this is example 04B, and this is another variation on it in that I'm going to use there's the carry flag. Well, you could do a comparison, okay, to see if you're greater than or less than. So the difference between this and the other previous program was, it's going to write out if it's equal, but also write if it's greater than or less than. So the way we do that is there's this JC. I guess it's jump if the carry flag is set. So if the so the carry flag is so it'll jump to label 3. So when it's less than, the carry flag set. So you can see here it jumps to label 3 when it's less than. So label 3 is over here, so it's going to write the string less than. Now if it happens to be greater than, it's going to run through this part here and say that it's greater than. The carry flag is 0 at this point, so it'll say it's greater than. So if it's greater than 80, it'll write out this message. If it's less than 80, it'll write out this message. If it's equal to 80, it'll write this message. So there's a lot of short jumps because you kind of have to jump around the loop, but the main loop is here and the main increment is over here. So we'll load that and run that program, and you could download these and look at these at your leisure. And if you take the data book, that'll also help to understand these instructions. So I hit the write enable. So I'm going to send the file. So we're going to go example 04B. So or 04B text. So this will load the program. So the program loaded. So now I'm going to do the K command, which is the check. So we're going to check it. So we're going to send the file, and we're going to load the program again. 04B. It's up here. So we're going to make sure it got loaded, and it's loaded. So now we're going to hit the J command to run it. So now it's going to say less than and equal and greater than. So we're going to try to catch it. This seems to run much faster while it's less text. That's probably why. The text really slows things down. So I'm going to look for when it says equal, the next cycle there. Okay, so I hit it right there. Didn't quite get it. So let me run that again. Right there. Okay, so when it's equal right here, that's when it's 80, less than, it's 7F, and greater than, it's 81. So that's kind of like an example of this statement where if you need to do math that's less than or greater than or equal, that's how you would go about doing that. So the last program I have for you is called example 05, and it's another little program, and what this does is it writes it to the internal scratch pad data RAM that's inside the processor. So I'm going to start it between 30 and 7F because the beginning of that is the registers, and it's also used for the stack and a lot of other things. But Anyway, so I'm going to write a value. I want to write a value, and the value I want to write is 0, 0. I just want to clean that, initialize that RAM, which is a good idea before you run a program to initialize it. I believe a lot of the compilers do that, but when you write an assembly, you don't do it. So when you first power up, the processor goes to basically any place. So the way this little program works is it moves, on register 1, I'm moving the start value. That's the memory that I want to start at, and AND is the last memory, so I move that to register 1. I move the value immediate commands to register A. So this is an indirect. I take what is in register A, and which is going to be 0, 0, and I indirectly write it into register 1, which is going to start at 30 hex. So now I'm going to do a compare jump if not equal. So if it's not equal to the end, register 1 is what I'm going to increment down here. So if it's not equal to the end, which is 7F, it's going to go to label 2, which is going to increment register 1, and that goes to label 1, which is the main loop. But when it eventually does hit 7F, it's going to go to label. It's going to go to A. It's going to jump here, so it's going to come through here and jump to label 3, which is right here, and then it's going to restart the monitor program. So anyway, we'll load that one, and just checking our communications there. So I'm going to hit the E command and hit our write enable, and I'm going to hit send file. So we went example 5. So it's another nice little program. So that's loading. The Intel hex file loaded. Very small little program. So now we're going to use our K command to test it. So we're going to hit send file. So this is very retro programming, but it's a good way to learn about computers rather than going to the big complicated computers these days, IBM PCs or Macintoshes, or iPads. This is a good way. You're not going to learn programming at that level, at the machine level. So this is a good way to learn it at the machine level. So we checked our program. So let's take a look. I'm going to look at that part of memory. So you could see in here between 30, this is our scratch pad RAM. And in that, it's all set to random numbers because I power it up. So now I'll hit our J command. And it goes back to the monitor. So now I'll do the D command. So now you can see it's all zeros now. So before it was random garbage in there. Now it's all cleaned out and set to zeros. So that's one way to initialize the RAM inside the scratch pad RAM for the 8031 or 8051. Anyway, thanks for watching this. This is an example, a little assembly language programs. Bye now.